On the morning of May 31, 1889, rain fell steadily on Johnstown, Pennsylvania. Water pooled on slate rooftops and ran in streams down unpaved streets. Smoke from the steel mills rose into low clouds, mixing with the mist that hung over the valley. The Kanemaw River, already swollen from days of rainfall, moved quickly between its banks, but it stayed within the channels that had been dredged and reinforced to accommodate the city's industrial expansion. Johnstown occupied the floor of a steep Appalachian valley where the Little Kanemaw and Stony Creek rivers converged. The valley walls rose sharply on both sides, limiting horizontal growth and forcing the city to build densely along the floodplain. Factories, rail yards, and worker housing pressed close to the water. The Cambria Iron Company's mills dominated the western edge, their blast furnaces running continuously despite the weather. On the eastern side, residential blocks climbed partway up the hillsides before the terrain became too steep for construction. The city's prosperity depended on its position at the intersection of water, rail, and iron ore supply routes. The Pennsylvania Railroad maintained extensive infrastructure here, including repair shops and switching yards that employed hundreds. The rivers provided water for industry and served as natural boundaries for urban planning, their flows regulated by upstream controls that had functioned reliably for decades. Rain had been falling since the previous day, heavier than usual for late May but not unprecedented. Residents went about their routines with minor adjustments, avoiding low-lying streets, moving goods to higher shelves, checking cellar pumps. The rivers were high, but they had been high before. There was no alarm, only the familiar inconvenience of persistent weather in a valley built to tolerate it. 14 miles upstream from Johnstown, the South Fork Dam held back Lake Kanemaw, an artificial reservoir covering approximately 450 acres. The dam stood 72 feet high and 900 feet across at its crest, an earthen embankment originally constructed between 1838 and 1853 by the Commonwealth of Pennsylvania as part of a canal system designed to compete with the Erie Canal. When railroads rendered the canal obsolete, the dam and reservoir fell into disuse and were eventually sold to private interests. In 1879, a group of Pittsburgh industrialists purchased the property and established the South Fork Fishing and Hunting Club, converting the reservoir into a private recreational lake. The club membership included prominent figures from Pennsylvania's steel and railroad industries who sought a summer retreat in the mountains above the congested industrial valleys. To accommodate their purposes, modifications were made to the original structure. The spillway capacity was reduced when a section was filled in to widen the road across the dam's crest, and fish screens were installed at the spillway outlet to prevent stocked game fish from escaping downstream. These alterations reduced the dam's ability to discharge excess water. The original design had included multiple spillways and relief pipes that allowed controlled release during periods of heavy inflow. But the relief pipes had been removed and never replaced, and the single remaining spillway was now partially obstructed and insufficient to handle maximum reservoir capacity. No professional engineer supervised the modifications, and subsequent maintenance consisted primarily of basic earthwork repairs to surface erosion. By May 1889, the dam showed signs of structural stress. Small leaks had appeared at various points along the face, and the downstream toe was visibly saturated. The structure relied entirely on compacted earth and clay to hold back 14 million tons of water, with no masonry core or reinforcement. Its stability depended on maintaining proper drainage and preventing overtopping, conditions that required constant vigilance and professional maintenance that the private club did not provide. Rain intensified across the Allegheny Mountain region throughout May 30 and into the early hours of May 31. Tributaries feeding into Lake Kanemaw swelled as runoff accelerated down forested slopes already saturated from weeks of above-average precipitation. Water poured into the reservoir faster than the single spillway could discharge it, and the lake level rose steadily throughout the night. The ground surrounding the reservoir had reached its infiltration capacity days earlier. Rain no longer soaked into the soil but ran directly over the surface, carrying sediment and debris into the feeder streams. The South Fork and its tributaries became turbulent channels funneling immense volumes into the lake, where the water had nowhere to go except over the dam's spillway or through its earthen structure. By dawn on May 31, the reservoir level was within 2 feet of the dam's crest. Club employees attempted to increase spillway capacity by removing the fish screens and digging an emergency channel through the dam's eastern abutment. But the rocky terrain resisted their hand tools, and the volume of inflow overwhelmed these efforts. Water began spilling over the top of the dam shortly after 11 in the morning, a clear indication that the structure had exceeded its design parameters. Engineers at the site understood the implications. Once water began flowing over an earthen dam, erosion would commence immediately. The compacted earth would soften and wash away, creating channels that would deepen rapidly under the pressure of the water above. Multiple observers sent warnings downstream, dispatching messages by telegraph and on foot to alert communities in the valley. Some messages reached their destinations, others were delayed or dismissed as exaggerated. The overtopping continued for more than 2 hours, with the erosion pattern spreading across the dam's face. By early afternoon, large sections of the downstream slope had been carved away, and water was cutting deep into the structure's core. The dam was no longer restraining the reservoir, but actively disintegrating beneath the weight of water seeking equilibrium with the valley below. At approximately 3:10 p.m. on May 31, the South Fork Dam failed. The breach began near the center of the structure where erosion had undermined the remaining earthwork, and the collapse propagated rapidly in both directions as the pressure differential overwhelmed the weakened embankment. Within minutes, a section more than 300 feet wide had been torn away, releasing the full volume of Lake Conemaugh into the valley. 14 million tons of water accelerated down a narrow gorge in a wave estimated at 40 feet high. The initial surge moved with enough force to scour soil down to bedrock in some locations and tear mature trees from the ground as it passed. The wave carried everything it encountered: boulders, timber, sections of earthwork from the dam itself, all moving together in a mass that gained debris with every mile. The terrain channeled the flood directly toward Johnstown. The valley narrowed in several places, compressing the water and increasing its velocity. At each constriction point, the wave rose higher and moved faster, building hydraulic pressure that would release catastrophically when the channel widened again. The distance from the dam to Johnstown was 14 miles, following the twisting path of the Little Conemaugh River through steep-walled gorges that offered no opportunity for the water to disperse laterally. Small communities along the route were destroyed in sequence. South Fork, the village nearest the dam, received minimal warning and was struck within minutes of the breach. The wave demolished structures close to the river and inundated everything within the narrow floodplain. Further downstream, the settlements of Mineral Point and East Conemaugh were consumed as the flood maintained its momentum through the restricted channel. The debris field grew continuously as the wave incorporated everything in its path. Buildings disintegrated into their component materials, which became projectiles within the flow. Rail cars were lifted from tracks and swept along. Bridges collapsed under the impact, adding their structural steel and stone to the advancing mass. By the time the flood reached the outskirts of Johnstown, it had become a moving barrier of water, mud, and wreckage 40 feet high, traveling at approximately 20 miles per hour. The flood entered Johnstown from the east at approximately 4:07 p.m. Residents in the lower sections of the city had received fragmentary warnings over the previous hour, but the scale of what was approaching exceeded any reference point for flooding they possessed. Most assumed a typical river overflow and moved to upper floors of their homes rather than attempting to flee to higher ground. The wave struck the Cambria Iron Company's wire works first, tearing through the industrial complex and carrying away machinery, raw materials, and sections of structural framework. The water then spread across the city's eastern districts, filling streets instantaneously and rising faster than people could climb. Houses built of wood were lifted from their foundations and carried along in the current. Brick structures withstood the initial impact longer, but many collapsed as the pressure built against walls, and the foundations were undermined by scouring. The Pennsylvania Railroad stone bridge spanning the Connecticut River near the center of town had been built to carry heavy locomotive traffic and featured 7 arches of substantial masonry. When the flood reached this structure, debris began accumulating against the upstream face. Sections of destroyed buildings, whole trees, rail cars, and industrial equipment wedged into the arches, forming a temporary dam that blocked the flow and caused water to back up across the city. The pressure behind this obstruction continued building as more debris compacted against it. The flood did not flow through Johnstown in a single direction, but rather filled the valley floor from multiple angles as water sought every available channel. Side streets became rivers. The current reversed in some areas as backed-up water sought new outlets. Buildings that had initially remained standing were struck repeatedly by debris moving in unpredictable patterns. The destruction was not linear but chaotic, determined by the interaction between moving water, stationary structures, and the accumulating mass of wreckage. Within 30 minutes, approximately 30 acres of central Johnstown had been reduced to debris. The downtown business district, the residential neighborhoods along the rivers, and significant portions of the industrial facilities had been destroyed or severely damaged. Thousands of people were trapped in partially collapsed buildings, clinging to floating wreckage, or attempting to reach higher ground through water still rising as the valley filled. The debris accumulated against the Pennsylvania Railroad bridge created a dense pile extending hundreds of feet upstream. Crushed buildings, uprooted trees, machinery, household goods, and human bodies were compressed into a mass 30 feet high in some places, held together by friction and the weight of water still pressing against it from behind. Trapped within this wreckage were dozens of people, injured and unable to free themselves from the tangled material. Shortly after dark, fires began burning in the debris pile. The source of ignition remains disputed, but the most likely explanation involves overturned stoves from destroyed homes, their coals still hot enough to ignite the dry portions of wooden wreckage as the water level began slowly receding. Once started, the fire spread rapidly through the compressed materials, which included petroleum-based products from industrial facilities and household fuel stores. The flames were visible from miles away, casting orange light across the devastated valley. The fire could not be controlled. Johnstown's water supply system had been destroyed, and the remaining water in the streets was too contaminated with debris to pump. Survivors on the hillsides could hear the sounds from the burning wreckage but could do nothing to assist those trapped within it. The fire burned through the night and into the following day, consuming a significant portion of the debris pile before finally exhausting its fuel and dying out. The full extent of the destruction became visible at dawn on June 1. The city's central district had been erased. In some blocks, only foundations remained to indicate where buildings had stood. Mud covered everything the water had touched, in some places several feet deep. The rivers had returned to their channels, but the channels themselves had been altered, filled with sediment and debris that changed the drainage patterns across the valley floor. Casualty estimates varied widely in the immediate aftermath, but systematic recovery efforts eventually established that approximately 2,209 people had died in the flood and its immediate consequences. The actual number may have been higher, as some victims were never recovered and others died later from injuries or disease. Entire families had been eliminated, leaving no one to report their loss. The demographic impact was most severe among the working-class residents of the lower neighborhoods, who had lived closest to the rivers and had the least opportunity to reach safety. Communication infrastructure had been destroyed. Telegraph lines were down, rail lines buried or washed away, and roads made impassable. For the first 24 hours, Johnstown was functionally isolated, able to send only limited messages to the outside world and unable to receive assistance. Survivors began organizing immediately, searching wreckage, treating injured, and establishing order in the absence of functional municipal authority. Water receded quickly from Johnstown, leaving behind a landscape transformed by displacement and deposition. Buildings that had withstood the flood stood surrounded by debris fields. Streets had been buried or scoured down to bedrock. The industrial facilities, even where structures remained, had lost their machinery and inventory. The work of reconstruction would require not just rebuilding, but complete excavation and remediation of the valley floor. Relief efforts began arriving within days, organized by the Red Cross under Clara Barton in what became one of the organization's first major disaster responses in the United States. Temporary housing, medical supplies, and financial assistance flowed into the valley from across the country. The scale of the disaster and the dramatic nature of the dam failure drew national attention, making Johnstown a symbol of both catastrophic loss and the capacity for recovery. Legal proceedings followed. Survivors and families of victims filed lawsuits against the South Fork Fishing and Hunting Club, seeking compensation for the destruction caused by the dam's failure. The legal theory was straightforward. Negligent maintenance and improper modification of the dam had created conditions that led directly to the disaster. However, Pennsylvania law at the time classified the flood as an act of God, a natural disaster for which no party could be held financially liable. The courts consistently ruled in favor of the club members, and no compensation was ever paid to the victims through legal judgment. The failure to achieve legal accountability did not prevent technical and regulatory consequences. Engineers and hydrologists studied the disaster extensively, producing detailed reports on the mechanics of the dam failure and the factors that had contributed to it. These analyses identified specific deficiencies: inadequate spillway capacity, removal of discharge pipes, lack of professional oversight, and failure to maintain structural integrity through proper drainage and compaction. The Johnstown flood became a reference case in civil engineering, cited in textbooks and professional standards as an example of what happens when infrastructure is modified without proper engineering analysis. Dam safety regulations began to emerge at the state level, establishing inspection requirements, maintenance standards, and professional qualifications for those responsible for operating water retention structures. The process was gradual and varied by jurisdiction, but the principle that dams required ongoing professional oversight and regulatory supervision gained acceptance in the engineering community. Johnstown rebuilt on the same site, restoring its industrial base and residential neighborhoods. The valley's geography had not changed, and the economic factors that had made the location valuable remained relevant. The city implemented improved drainage systems and flood control measures, though truly effective protection would require infrastructure investments that took decades to complete. The lessons were architectural and regulatory rather than locational. The city stayed, but the standards for the systems surrounding it evolved. The South Fork Dam was never rebuilt. The lake bed gradually returned to its natural state, and the ruins of the dam remained visible as a physical reminder of the disaster. The site attracted no new development and required no memorial marker to indicate what had occurred there. The absence was sufficient.